One half, my dude. Yeah, it was. You did the middle one, you got the two outer ones, you just one half, so it's two. Oh, wait. Logan. Logan did it wrong too.
Oh.
Oh, you're trying the other one? Oh, you have a hair in your mouth. That's never fun.
Sorry, everyone.
Should really stop eating hair. So I've got what I think maybe the slope field ought to look like roughly up there. So those that are either done or you're getting close to the end, maybe check and see if we agree on what the pattern ought to look like.
That's -1.
Oh, you started dividing.
No.
Or
Just when I put the little dashes, I went over 4, not up 4 on accident.
got it. So you did run over rise instead of rise over run. Got it.
Yeah.
Got it.
Oh, I'm doing this right.
So be careful.
Cool.
So think of, like, if somebody could recognize a pattern on number 2, what pattern would allow them to do number 2 in a fairly quick way, a fairly quick amount of time?
It's only dependent on Y values.
Therefore, the pattern would be? How would you describe the pattern? I mean, you're totally right.
Symmetrical about the X.
I don't know if I would use the word symmetry. I mean, there is some...
90 degrees, yeah.
There is like some sense of symmetry there. I agree with you.
Way off.
But like Logan said, if dy dx depends only on y, that's a key thing to notice. But that sets your pattern up. How do I say this? In what orientation do you see the same slopes?
Oh, cross. The X.
What do we call this?
Horizontal.
Horizontal. There we go. There's a good pattern.
I'm better and I know it.
So maybe you notice that in a horizontal pattern, all of the slopes were the same. This is a characteristic of a slope field that depends only on y. Maybe I think on the intro video, I think I had one where the slope field depended only on x. And what kind of a pattern would we see there?
Vertical.
Vertical, correct. Okay. Do you guys have any questions on any of my slope field marks up there? Maybe there's some agreement, maybe some disagreement. I don't know. Is there anything I can do to explain or help where that graphic came from? Okay, so then how about a solution curve drawn through the point 0, 1? Obviously, the point 0, 1 is right there. And so the idea of drawing a solution curve, there are a couple of requirements. A solution curve, number 1, has to be a function. It's got to be a function. It's got to go through the initial condition, right? It's got to go through that. And it's got to mimic the slopes that you see in the slope field. So can I give you a really terrible example of a solution curve? So this one goes through my initial condition, but do you see how it does not mimic the slope field at all?
Yes, sir.
Doesn't match it at all. It's going downhill when it should be going uphill, right? Here's another example of a not so good solution curve. Now this one comes a little closer to mimicking the slope field. What's wrong with this one? It doesn't go through the point, correct? So here is a good example, or my attempt at a good example. Something like that, where you can see how we're really kind of following the pattern that we see within the slope field. We're going through the initial condition. And also notice that it's not a game of connect the dots. So it's not this purple effort. So it's not like we go where we try to go through every single dot. As a matter of fact, I would say in most cases you want to avoid all of the other dots if you can, in most cases, because we only really know that the curve goes through that initial condition of 0, 1. We don't know that it goes through any other points, so I would avoid the other ones as best you could.
So
Okay.
like each point on the x-axis, like it's like 0.5.
Each point on the x-axis is like 0.5. Is that what you said?
Yeah, that's right.
I don't think so. I would say that each. So tell me why you're saying that.
Because it says like 0 and
0, 1, yeah. So I would say that I would more say that every little mark is 1. So like this would be y equals 1, this would be y equals 2, this would be y equals -1, y equals -2. This would be x equals 1, x equals 2, -1, -2. That's kind of how I saw it. Is that kind of what you're getting at?
yeah.
I think they're probably just all whole units. I don't think there's any 0.5s. So like this right here, like this point would be the point 1, 1. This would be 2, 1.
I thought it's like an interval.
We thought what was an interval? Oh, you thought this was an interval?
Yeah.
Oh, okay. So you see through is indicative of a point. Like a curve going through something, you'd say the curve goes through a point.
I see.
Yeah. Got it. Okay. Can I show you one other bad example of a solution curve?
Yes, you can.
Okay. So if I just left that as is, and then if I drew this in, what is so wrong with that? It's a really nice looking curve like the other one.
It's not a function.
Not a function anymore, right? I've got to pick the part of the solution curve that allows it to remain a function. Once I start making it not a function, I got to stop. Okay. If you haven't already looked at number 3, it's a little more adventurous. Give it a shot.
Let's do it.
dy dx equals x minus y.
This is what mine looks like, but I'm not sure if it's right. Just a little.
You should be able to see patterns even in this. I mean, there's definitely some. So consider.
Let's do the origin, because that's fun. Is it gonna show? Well, I don't.
This is whack.
-1. I don't. Oh, it's the
Bless you.
I think you're beautiful soul, Nick.
Thank you, Margaret.
Nick does have a beautiful soul.
Thanks, guys.
Isn't Nick the best? Nick is the best.
What's going on?
The best at what?
Everything.
Everything. Okay. Nick, that's a rare compliment, truly.
Thank you.
I don't. Oh. Hold on. Oh, I think I did that wrong. You know what? And there it is. Here it is. I got it. Okay. -1. I don't know how. Oh, I did that right.
This is kind of cool.
I'm kind of figuring it out. Is it that?
I'm just gonna get this one on a second.
Okay.
Feel good about that.
Mine turned out kind of pretty too. Sometimes it doesn't.
I'm contemplating.
I definitely recommend a pencil. You
Okay.
need a pencil?
No, I can have a pencil. I got one.
Are you sure?
I think I got it. That's what I got.
Okay.
So you just, don't you just, am I crazy, but don't you just?
No, you moved on to number 4.
And that's your slope?
That looks kind of
Just plug
Wait,
it in.
right?
This is kind of wrong.
This is what I did, but it looks kind of wrong here.
So, you guys have the, okay, so you have the
Negative.
I mean, yeah.
same looking slope. I'm just looking at the slope field right now. It's like very
Just
similar.
add them together.
Pretty much
Minus
the same,
2
isn't it?
and negative 4.
Yeah, that's how your slope
And
field's not the
negative
same.
1 minus 4.
Differ on, well, so you guys pretty much agree on this part, but then Peyton's got it kind of bending down. Like probably,
So it's 0, 0,
you've got it kind of
0.
doing that number right there. I mean, I think, number
One
one, I think your
negative
slope
one.
fields both look
Right.
pretty good.
So
So that's a good start.
If you add 1,
So let me create.
One negative one's 2. Oh.
Side.
and then you subtract 1 from your 1, you're gonna be at 0.
What do you think?
Nope, you're gonna be at 2.
Consider, consider the points,
Welcome back. No,
along-
see you next
Alright,
week.
hold on, time out.
consider the points along this line of slope fields, right? So this line right here. And think about what on the graph of the solution curve, what would that be? Like what feature would that be? Yeah, because along that line, like all the slopes, like they're all, it's like collinear slopes, right? They're all pointed right at each other.
0, 0.
So what kind of line is that?
And I just needed
It'd be a totally straight line, yeah, what else?
And then he was like,
And I agree would have a slope of 1, what else?
sorry, I didn't know.
It's got kind of an advanced, it's an advanced feature, something that maybe like a pre-calculus student would know, an algebra 1 student would never.
Right here is. This is.
Like nice one.
Well, an algebra 1 student would definitely know that that's y equals x minus 1. Well, I think that my algebra 1 students right now, I bet you probably 70% of them would have that in like 10 seconds. The other 30%, maybe a mixed bag, but they'd have it. But they would not know what to call it for real,
No.
because they've never seen it before.
Here.
I'm not.
It's an asymptote.
Oh.
Diagonal slant asymptote.
So just keep looking. Why was Margaret the page on the?
It's gonna like approach that over time.
I mean, like,
So, what's kind of cool is it kind of does this.
All right, so here is my representation of the slope field.
No way, that's what I had kind of.
What do you think? Pretty close? Did you guys notice that this had a lot of diagonal patterns to it?
Yeah, but if it's like -1, -1, 0, so how do I?
We'll get to that in a second. We'll get to that in a second. Any questions on any of the little slope field marks? Essentially, isn't this like advanced point plotting?
Yeah.
And I'm not like trying to minimize what it is because you have to know what you're doing. But for you guys, it's like advanced plotting of points. Like you find the slope here and you plot that and so on and so forth. So I'm glad you're doing okay with that. As far as the solution curve goes, the solution curve does go through the point -1, -1, which is right there, which just as mentioned, just so happens to be where our slope field indicates a slope of 0, right? So as we think about how this goes, I'll show you some bad ones. Do you see how this would be incorrect? Do you see how that does not mimic the slopes at all?
Yep.
All right, so here's another one that's maybe not so good. What if I did, oh man, it's hard to write a bad one here. Got to think about this. So, right here, you could build this out like this. I'll try to just build it up for you. Do you see how this, we're just going to be flat right there? But the minute I move to the right, aren't I headed right towards this line? So I can't just go straight right. What I've got to do is I've got to start to try to bend towards that, as I get over there, I'm going to be mimicking the slopes that I see all along that diagonally looking line. But at the same time, I can't just shoot off to the left horizontally either, because as I move to the left, I can see that the slope fields are going to a negative slope. So I've got to kind of curl them to mimic that. So maybe something like that. This looks pretty similar to some that I saw. This looks pretty reasonable, to be honest with you.
Does that literally become linear?
So this table, please don't say anything. What kind of a pattern do you guys see here? I think, Jack, this is what you're getting at. Does that just become linear, right? What do you guys see in that highlighted red area?
Same slope and a diagonal.
And it looks like a diagonal with same slope. It looks like a line, doesn't it? But clearly, once you move off that line, there's curvy stuff everywhere. It's a slant asymptote.
Why did that take us so long?
It's a slant asymptote, that's right.
So what's with the slopes going on down there at the bottom?
Well, so if I wanted to see a different solution curve, and I said, you know what, the solution curve actually does not go through -1, -1. I want a different one. And my solution curve would go through, let's say, 1, -2. So that's down here. So that solution curve would look a little bit different. It would obviously get very steep down there. It would come up to here. We'd head up towards that slant asymptote, and then we would bend to kind of follow it the closer we got to it.
How do you know that it's a slant asymptote?
How do you know that it's a slant asymptote? Let's see here. Well, because as you move towards the far, like especially if we were to expand this, and I wouldn't want to do this to you without a computer, a calculator of some kind that could draw the slope field for us, but if we expanded this to be even bigger, what we would see is that as we went to the far right edge of the graph, all of the slope field marks are pointed towards that line. Like, can you see how all of the slope field marks, every single one of them, are pointed towards that line? But as we get closer and closer to the line, like especially if we filled in all these little gaps in here, like if we did fractional slope fields, like we plotted like 1/2, 1/4, 1/8, 1/16, we'd find that the closer we got, like in this lovely purple gap, every single one of those slope field marks starts to bend to mimic the line, which is simply just a characteristic of what an asymptote is, right? Like a horizontal asymptote, which we had on the previous one, or a slant asymptote. As you think about long-term behavior, don't all the points start to follow that? And as we can see that even in this like fairly rudimentary slope field, we can see they're starting to bend towards that even with this, even with just like the plus or minus 2. So it's just that characteristic of knowing what an asymptote looks like on a graph and seeing that trend towards it to mimic it is what's happening. We could expand this big time. You could really see it. It would just take forever if we didn't have a computer. Okay, what else can I do? Okay, so I think there's one more for you to draw. So if you would take a look then at number 4.
Wait.
Well, there's a pattern. Wow, that is beautiful.
You're beautiful.
You're beautiful, Art.
You did not just. You have no right.
Come get your man right here. I can go 2 different ways with this curve even through the given point.
I could kind of go up vertically, or I feel like I could go out horizontally a little bit more too. Which one? Can you help me
This will
discern?
be worth, well, this would be worth talking about. Continue to think. Let me get mine sketched real quick. I think you have definitely identified something worth talking about,
circle?
but I don't think you can go, I don't think you really have a choice. We'll get to that in a second. I don't think there really is an option.
Wait.
Do 1, 1. Okay.
You're the only person on my Snapchat that still sends me streaks. Everybody else.
Like, don't talk to them.
Crazy is that this turns
Wait, I figured it out.
Can I do like a bunch of little slopes field thingies?
Maybe certainly you can try, like you could fill in the halves or the fourths if you think that would help you.
We didn't know.
I'm not gonna respond to any more of them.
I'll send you an
Generated streak snaps are just such a shot to your confidence.
I'll send you like an
Person
individual.
wants to be friends. Oh. Fake
I'll send you an
friendship.
individual.
Fake friendship.
Did you guys have something like this?
Yeah, that's exactly what happened.
Fairly nice looking graph, I suppose. Do you guys get the same sort of thing? So one thing I'm looking at Peyton's and Justin's.
It's a Mr. Lowther thing.
What's a Mr.
Okay, so
Slope fields.
right here, you guys check this out, please, Santi, Nick, make sure you see this. So why on earth would I leave the x-axis just blank?
Because it's undefined.
What's undefined?
The
The slopes are undefined right there, that's right. So it's because, of course, all the y coordinates there are 0, and our slope field is based on x over y, so x over 0, essentially. So if you ever have a slope field mark that's going to be vertical, don't draw anything. Like, don't even try to get it vertical, because right there the slope does not exist. And so because of that, what we're going to do is we're just going to leave it completely and totally blank. Is that okay? Okay. So again, like from a reader perspective, like that's how we're directed to deal with that. You know, if it's supposed to be vertical and they wrote anything, they don't get credit for that part. So just be careful with that. So as far as a solution curve goes, through the point 1, 1, we might do a couple of solution curves just to be interesting here, but 1, 1 is right here, isn't it? Oops, there we go. Red point 1, 1. So I heard a lot of you say, "Oh, it's a hyperbola." Hyperbola, yeah, right?
That's not a function.
And hyperbolas sometimes they have parts that are not y function being y is a function of x. But what other graphical feature do hyperbolas have? Well, they sort of are parabola-y looking. They do have asymptotes, right? What kind? Would you guys agree with me that our initial condition is right on one of those slant asymptotes?
Yeah.
It's right on it.
Wait, so it's a line.
So our solution curve is actually a line. It would actually describe the diagonal slant asymptote. So that would be your solution curve here.
Is there a hole at like 0, 0?
No,
It just goes through it.
this goes right through because it's the asymptote. Let's do another one or two just to make it a little more interesting. What if you had a solution curve and you were told that the solution curve goes through, I don't know, how about 0, 1? Think about what that would look like if it went through, the solution curve went through the point
Oh, there it
0,
is.
1. Sir.
How can it be that that line is the solution if the slope doesn't exist at 0, 0?
So the function definitely exists at 0, 0. Right? You get the slant asymptote, right?
Yeah.
The slope doesn't exist.
So how can that be that? How can that be
So the red, so the red graph or the green one that I'm about to draw stands for the actual solution curve itself, like the function that if you differentiated it, you'd get this derivative. That make sense?
Yeah.
And so you could have you can have a solution curve that absolutely exists. So I guess what I'm trying to say is you can have a graph that is nice and continuous and very beautiful and everything, but not differentiable, right? So like a vertical tangent line would be a nice example, or an absolute value graph would be another example where the slope of the graph might not exist, but the graph itself is nice and continuous and beautiful. No problems at all. That makes sense? Okay. Hey, did you guys get sort of a parabola looking thing here? I think the green solution curve would look something like this. And it would just continue on over to here and kind of bend to follow that horizontal asymptote. Can I show you one more?
Sure.
One more that's a little trickier. I'm going to go with purple here. What if you had a solution curve that went through the point, I'm going to say -1, 1. Think about what that solution curve could look like. Oh, no, shoot. Sorry. My bad. Yeah. Check that. Let's do -2, 1. That's the one I want to do. Solution curve through the point -2, 1, which is right there. Oop. Right there. Think about how you could draw that. Say one more time, Forrest.
I don't really understand, like, does that make any difference? Because, like, it's the same graph.
Does what make any...
Like,
So we're just graphing different parts of it. So remember that a solution curve, A, has to go through the initial condition. B, has to be a function. Right?
Yeah.
And so since the graph has to be a function, I can't graph the green part and graph the purple part as part of a single solution curve. They're different ones, right?
Oh, okay, I see.
Does it make a difference? Yeah, like so if I look at this purple point over here, you can see that's not part of the green graph at all. So that's going to be a different portion of a potential graph than the green one was.
Okay. I see.
So depending on what that initial condition is, your graph could look very, very different. Okay, can I show you the most common error here? Here we go. This is the most common error. You start here and you draw this. You draw this nice curve right through here, and then you just continue on your merry way through there, and you say, "Hey, there's my solution curve."
Function, boy.
It's not a function.
Gaslit.
So for it to be a function, wouldn't you have to pick the upper half or the lower half? Which one do you pick? Why would you pick the upper half? That's where the initial condition actually is. Yes.
This is...
So I would do this, and customarily what we do is we put an open circle right there, saying that because there would be a single point of a vertical tangent line right there on the x-axis, we'd go right up to that, but not actually include it. So that would be probably the best way to represent that, and we'd be done. How we doing?
So can you explain me something?
I will in just a second. Hey, if you're good with that part, why don't you guys move on to number 7, which is kind of a matching game where you're trying to match the different slope fields up with differential equations.
Last year?
Yeah.
I did. Okay.
So
It's a shame.
how do I? 'Cause I feel like I could still. So I know it's the initial condition is right there, and I got to stay above the x-axis. I feel like I could still go through and do other things. How do I discern that as just that?
Does anyone know?
I feel like I could. Well, so the problem with that is that as you pass through, say, like this vertical phase, like this part right here, you can see that, like up here, this was a slope, I think, of -1/2. This is a slope of -2. So you can see this pattern, like the closer you get to the x-axis from above, the slopes are getting steeper negatively, right?
Okay.
So this is -1/2, this is -1, this would be like -2, down here would be like -4,
Gotcha. Yeah.
and you'd have to admit, whoa, wait a minute, that's,
Then you'd have to.
there's,
really
it would be
take a
doing
dive.
one of these guys, which wouldn't fit with the rest of it.
Okay.
Yeah.
Gotcha. Thank you.
Yep.
Okay.
Okay, matching. So some of these might come fairly easy to you, one in particular. Others might be a little tougher. I don't know. Let's see. What do you guys think for A? A went with 7, 8, 9, or 10. Why did you pick 9? So did you just plot points, or did you look for a pattern? What kind of pattern do you see? Hello, hello. What kind of pattern do you see on A?
They're all the same, like horizontal.
Yeah, there it is. They're all the same horizontally. And so if they're all the same horizontally, that always goes with dy dx depending only on what? And do you see how all of our options depend on either x or x and y, except for number 9? So based on just process of elimination, I would say for sure I agree with you that number 9 goes with A. How about B? What do you think about that? 10. Okay, so can we do just the vertical pattern thing here, right? Because you do see vertical patterns, but don't 7 and 10 both depend only on x? How did you differentiate between 7 and 10? So C looks cyclical, doesn't it? Looks periodic or whatever. Yeah, so C would probably go with 7. Of course, then leaving B to go with 10. And then I think number 8 should be the easiest one, oddly enough. Why? We just did it, didn't we? You recognize it? It's the same differential equation. And process of elimination would lead you to D. So did you notice that A, only horizontal pattern because dy dx depended on y? B and C were vertical because dy dx depended on x. And then D had this diagonal thing going on because dy dx depended on x and y. You'll often see that that's the case. Okay? I think there might be one more matching activity to do. So let's do it. Yes, there is. This one's a little tougher.
Oh boy.
The reason why this one's tougher is because we don't have differential equations to match to the slope field. We have solution curves. So, big hint, we actually did this exact one last year, but usually people still have to think. Okay? So I've given you solution curves. So if you know solution curves really well, like if you know your families of functions, your parent graphs, that whole thing, this one might actually be pretty easy for you. If you're not really strong with your parent graphs, this one could be tougher than the last one, perhaps. It's not. It's. Oh no! Oh wait a minute. Are you referring to? No, you're right. I thought you were referring to the function.
Yeah, no.
That's confusing.
It's
You
the-
should have said capital letter. Yes.
Yes.
Sorry.
Let's go.
Sorry, I gave you a moment of
No,
panic
you're
there.
good. You're good. I was really. You threw me on turbulence there for a second.
Sorry about that. Oops.
So it's wide.
It's wider than negative again. Raw XD.
Or raw XD.
Even the X.
It is. Have you seen that video where he's like, like a guy stepping to like a sea of just all these kids sitting on the ground and all like he's going raw XD or raw XD. It's a funny video.
Okay.
And they're all like, what?
If you're really good at parent graphs, this one's probably already over. However, let's say you're not. Let's say you're not as good at parent graphs. Listen up, please. Shh. Listen up. Here's what you could do. It's a lot easier to compare these things when you have differential equations as opposed to solution curves. So if you wanted to, couldn't you go through on all these and just do a derivative and say for A, for example, it would be dy dx equals 2x. And for B, dy dx would equal e to the x, et cetera, and then just kind of compare by plotting some points. You could do this. So for example, A, if dy dx equals 2x, wouldn't we need to see a vertical pattern? Well, we do. In fact, they're all going to be nice vertical patterns, but we could plot some points. If this is 3, wouldn't you guys say that this is about 1? And then right in here somewhere is about 2?
Yeah.
Approximately? Okay, so if dy dx equals 2x, then when x is 1, the slope would be 2, wouldn't it? Follow with me, please. If a is right, wouldn't the slope at 1 be 2? And it might be the case, but then when you look at 2, you realize, well, if that's the case, then wouldn't the slope at 2 have to be 4? And so that would mean that these slopes over here would have to be steeper than these slopes over here, and it's the opposite pattern, right? So it's definitely not going to be A. B. If you plug in a 1, then a 2, then a 3, wouldn't we want to see an increase in the slope? The slope would go from not very steep to steeper to really steep, right?
It would.
And we see the exact opposite pattern. So it's not B. Weight what? That's the classic question. Weight what? If C was the answer, every single slope would be negative, wouldn't it? Because it's negative e to the negative x, and they're all positive up there on the graph, so it's not C. Was D the easiest to eliminate, maybe? Because you don't see any of this cyclical periodic motion, so it's probably not D. Which leads us to E. The differential equation for E is dy dx equals 1 over x. And this actually fits really nicely, because as x gets bigger, doesn't 1 over x get a little bit smaller, but remain positive, doesn't it?
Yeah, it does.
So, please don't pack up yet. I don't know, your sense of timing is terrible. There's 5 whole minutes left.
That's 300 seconds.
Yes, let's use all 297 left. Would you guys be okay with a solution curve that looked something like that? Does that seem like a reasonable solution curve?
Yes.
For those that are really good at parent graphs, shouldn't this look a lot like a natural log function? If you put kind of the bottom part on there, it becomes a little more clear. It looks a lot like a natural log, which is, of course, the inverse of E. And E would have looked like this about. And you can see that nice reflection along the line y equals x. So you can put it together a little bit further. And you can also see why y equals e to the x wouldn't work very well either for this particular slope field. So finally, after all that hard work, you would arrive at E. Or, if you know what your parent graphs look like, it took you like 5 seconds, right? Because you're like, nope, nope, nope. Oh, ln, looks like ln, I'm done. So just another encouragement to continue to dig into those, and hopefully it'll help you. Because even on like an AP test or something, if you had like 2 questions where you saved 2 minutes on each question, that's valuable, right? That's huge. You just set yourself up for success. Okay, so